So another observation, just real quickly, if we look at our same problem, if we detach this guy from the side and draw a free body diagram like you would in statics, right, or engineering mechanics 1, so we have P1, P2, U1, U2. Well, we know P1 is equal to the area times the stress on there. And the stress, right, using Hooke's law is E times the strain, right? And if we use an engineering definition of strain, what's the engineering definition of strain is the change in the change in length, or the change in displacement divided by the original length, right? So then we'd have U1 minus U2 over L. So that is AE over L U1 minus AE over L U2. Right? Likewise, P2 is the area times the stress on phase 2, which is the area times the Young's modulus times the strain. And the strain, using the same definition, U2 minus U1 over L. So that's AE over L U1 plus minus AE over L plus AE over L U2. And so then if we wrote this in matrix form, we'd get so we get the same element stiffness matrix that we did when we took the very systematic approach of going through all the finite element stuff, right? Except one thing, right? So you might ask, why'd you make me do all that, right? Why do we go through all this, develop the weak form, all that? We ended up, could have drawn a free body diagram and got the same result. The caveat is this. We use engineering strain. Well, when we use engineering strain, we're implying that there's a constant strain across the element, right? And that may not be the case. There could be a distribution of strain across the element, right? And so there's not, this is the reason for doing it the other way, is because the other way, we take a systematic approach and we don't make the assumption on what the strain is to the element. We introduce it through the interpolation, right? So this is the equivalent. Stiffness matrix is for the linear interpolated case, right? But if we go quadratic, there'd be something different. If we go cubic, there'd be something different. And in those cases, then we could model a variation in strain across the element, right? So the point here is that it is consistent in the simple case, but there's no systematic sort of free body diagram way to do the more complex things, right? So